Okay, so now we have to do these processes. So we're going to do the first 6 today, and we're going to do the 7th on Tuesday. Trust me, it's way more simpler than what it seems. Are we ready? Right? It's so scary to look at. I know. So look at how many there are, right? But look at the definition. Look at what it's asking you. We are now going to deal with processes an ideal gas undergoes. Okay, what do we think are the different processes that an ideal gas can undergo? Constant volume, constant pressure, constant temperature, adiabatic, blah, 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 right? So let's start at the beginning. The first one. So ideal processes, ideal gases undergo. Processes, ideal gases undergo. Okay, here we go. Number 1. Work done. What's the definition of work done? What different kinds of work could we have? There's only 2 basic kinds. What are they, guys? Compression and when we have compressional work, we call it work done on the system. And when it's expansion, we call it work done. When we have work done on the system, is the internal energy going to go up or down? Up. Is the temperature going to go up or down? Up, right? When we have expansion work, is the internal energy going to go down or up? Down. And then is the temperature going to go up or down? Done. And usually those kinds of work are expressed on a PV graph, where this is the V and this is the P. And what you do is, whatever that work looks like, you find the area under the curve. We've done this, right? If it's geometrical, you use definitions of area. If it's not, then you just integrate. That's basically what an integration is. Okay, number 2. So I'm going to mark out number 1 done. Oh, I should pick a color.
Green.
Green. Done. Number 2, a gas undergoing a cyclic process. What is a cyclic process? Cyclic process? A cyclic process is A to B to C to D back to A. If I have to come back to state A again, what can you tell me about that state? Must its temperature be the same? Must its volume be the same? Must its pressure be the same? Right? So can I then say delta U must be 0 for a cyclic process? So if this is true, does the first law of thermodynamics say 0 equals Q plus W? So in a complete cycle, delta U must be 0. Number 2 done. Now, what is the next definition is free expansion. What is a free expansion? Number 3. Free expansion.
Do you have something against purple?
No, I'll do purple next. Expansion process. What's a free expansion process? So this is a free expansion process. Copy. Paste. What's happening here?
You're shrinking.
Oh yeah, I'm shrinking the image, but what's a free expansion process?
The gas expands to fill its container.
Yep, that's it. A free expansion is a process by which a gas freely expands to fill any available space. Okay, in this case, for a free expansion, still going with the stream, work equals 0. Why? Because we didn't lift any weights. Do you remember our conversation about the piston? When the piston just expands freely, does it do any work? Any useful work? It's like an elevator going up by itself. Didn't do any useful work. So a free expansion of gas involves no work, useful work. And also, Q equals 0. No heat is added if it's a thermally isolated system, which means from the first law, if W is 0 and Q is 0, what should delta U be?
0.
Whoa. Step 3 done. Okay, number 4. What is it? Constant volume process. Now I'm going to do purple to make you guys happy.
Yay.
Purple. Constant volume process. What is a constant volume process called? Isochoric. And what do we know about it? Delta V equals 0, which means what? No work is done, which means first law can be written as
0.
woohoo. Step 4 done. Next is a constant pressure process. What do you think happens in a constant pressure process? Yes. Constant pressure process. Which means what? Delta P equals 0. Which means W can be written as PdV or P V2 minus V1. If we have V1 to V2 here. That true?
Mm-hmm.
So then how do I write my first law? Delta U equals Q plus W. Ha, my Q became funny. I'm going to leave it. Oh, step 4 done.
5.
Oh, yeah, that was 5, right? Yay. And last but not the least, isothermal. Okay, so for isothermal, what do we know?
Delta T equals 0.
Delta T equals 0. Isothermal. What do we know? Delta T equals 0. Which means, from the first law, 0 equals Q plus W. Now, for the ideal gas, in this situation, we can't just leave it here. W actually equals negative P dV. Okay? And from our ideal gas law, we know PV equals, do you want to nRT or kRT? nRT? Fine. So may I rewrite this as P equals nRT divided by V? I'm going to plug this value in here. And that will give me W equals P nRT over V dV. Oh no, why am I putting P back in? Sorry. So that will be what it is. Okay, is N a constant? Is R a constant? Is T a constant? There's no change in T, right? So I'm going to take these all out. Minus nRT integration 1 over V dV. What is the integration of 1 over V? Log, right? The natural log. Minus nRT natural log of V from V1 to V2. Or W now becomes nRT log of V2 over V1. Do we all understand properties of log? Do we all get how we got V2 over V1? No, don't trust me. Make sure you know how to do this, because this is going to come back and haunt us.
Okay, then can you explain?
I can explain it. So basically, what is happening between these steps is that we are integrating 1 over V dV, right? So integration of 1 over V from V1 to V2 is natural log of V2, natural log of V from V1 to V2. How do you open the limits of integration? Log of V, natural log of V2 minus natural log of V1. And then properties of log says log of A minus log of B equals log of A over B.
I forgot that.
If there was a plus sign in here, then log of A plus log of B will be log of A times B. That's just a property of logs, okay? Which then leads me to be able to write log of V2 over V1. That's how I got from here to here. Are we good? Well, okay, hold on. Let me go back. So all of these are done.